In the last talk, we are going to talk about some performance optimization for the zkEVM. So I think first things that we're going to, I'm going to describe like what's happened inside the Halo2 provers or inside the Plonkish provers with the KZG commitment. And then talk about like what kind of optimization we did and then what's the performance number we have so far achieved. So first of all, like I think previously also Yingtong showed this kind of diagram of what happens inside this Halo2 or Plonkish circuit to do. So first of all, at the top level, you have the circuit arithmetization, where you write the circuits. You define all of your custom gates, the lookup arguments, and then the permutation you're going to do to constrain circuits. And then second, like we will convert those circuit arithmetization and then define it becomes into the convert them into the polynomials, and it becomes the relationship between the polynomials or the constraints between the polynomials. I call it like the polynomial identities. So you can see in this step, in the second step, so we just have a lot of equations of those all of those polynomials, and those will be the constraints that the prover is trying to constrain and then generate the proof around that. And then last thing, so what you're going to do is using some of the polynomial commitment scheme to do that. And then in our particular case, like you probably need to commit to the your polynomials and then open at a random points that are going to check in the verifier. And what we're using for the polynomial commit scheme is KZG, the commitment scheme. There could be like some other commitment scheme, for example, the IPA used in the original Halo2, and then there will be Fry as another commitment scheme. But like in our prover we are using for the zkEVM, the scroll or like PSE zkEVM, is that we are just using the KZG commitment scheme. Okay, so actually Yingtong has already covered a lot about the Plonkish arithmetization. So you have like different types of columns. You have advice columns that's going to put any arbitrary witness data into those advice columns. And you have fixed columns for some fixed data you can put into that. That could be like already pre-processed before you in the verification and proving keys. And then there are selectors that control all of the custom gates and also the lookups you're going to do. And then there's some instance column inside the circuit which is going to hold any public input data inside that. And then there's three major primitives, basically primitives inside the Plonkish arithmetization. So one is the custom gate. So you can define any constraints or relationship between all of different cells with rotations. And you can do the lookup argument with a very powerful thing. So you can prove like a column which had all of the value inside of one column is belong to some of the table columns that you predefine or you can generate through the device. And then the last thing will be the permutation, which you can copy data from previous rows to the next rows. Those are the primitives you have in the Plonkish arithmetization. Okay, so next we're going to talk about, so by the way, so when we're building the zkEVM circuits, we mainly use the first two, the custom gates and then the lookup arguments. So the permutation we didn't use a lot inside that because one is the EVM circuit has a lot of flexibility inside that, so the permutation need to be fixed per circuit. That's why like the permutation is not heavily used. So I'm just going to talk about more about the custom gates and lookup argument. So first, the cost of adding a custom gate. So let's take an example. You have this, you define this T-shaped custom gate involve like the 3 elements in the first row and then the 1 more elements in the next row. And you can define this, the constraint is that VA multiply VB multiply VC minus VB equals to 0. And then that will be then translated into this polynomial identity, which is called like A1, which is defined as like the column, like when you commit the column A1, it will become A1x as a polynomial for this column, and then multiply A2 and then multiply A3 minus A2 omega x equal to 0. And here the omega x basically defines like this is the next row with regard to the previous 3 rows. And then because this custom gate may not apply to every rows in these 3 columns, so that's why you have a selector column like and then when you can set a selector to 1 at that rows, so that means like this custom gate only check the row we have like here marked as 0 in the red regions, And then that's change like the, that's will be also corresponding change the polynomial identity here, so that you need to multiply one additional polynomial into the previous polynomial we have. So that means like this polynomial will only check whenever the selector is set to 1 at that row. Okay, so then that means like if you in total in your circuit, if you have dg custom gate arguments there, then you will end up into dg number of those polynomial identities in your final proof you need to work on in the prover. Okay, next thing, we'll talk about the cost of adding a lookup argument, sorry. So for example, let's say we want to prove this, all of the value inside the A1 column will belong into the values into the T1 column, which is some table column there. For example, see like the here you have like the, for the A1 you only have value 1, 2, 1, 2 or 1, 2, 3, like there has arbitrary values, and you can have duplicate values. And for this table you only have 1, 2, 3 are all the values you can have for the A1. So what they're going to do, like this could be like there are some different versions of this lookup argument. So I'm talking about the one is specifically used in the Halo2. What you're going to like in the Halo2 is that you will generate 2 new columns from the A1 and then T1 into this A1 prime and T1 prime. So you're going to do is like for the A1 column, you're going to sort every value inside A1 column and then create these new columns. And then for the T1, you kind of like sorting this column into like the new things. But what you do is like you will map this value 1 like into the first appearance value 1 inside the A1 column. And then rest of them will just pad with 0. And then you will put like the value 2 at the same row as the first value appear in the value 2 inside the A1 prime column, and then so on and so forth. That's how you generate this A1 prime and T1 prime columns. And then second step is that you need to constrain this A1 prime column is actually using all of the value inside the original A1 column to construct this new A1 prime column, and same for the T1 prime columns. So you need to add this additional multi-set check to constrain the A1 prime and T1 prime from the original A1 and the T1 columns. That means like these 2 polynomial identities you need to add in your final proof. And then third thing is you see constrain. This is finally the constrain the value that's all of the A1 value will belong into the value inside the T1 prime. So what you're going to do is like you can check all of value inside A1 is either equal to your previous row value, or you're equal to the same value in the T1 prime column. And then you will have some initial condition check, which is like the first value need to be same. That's like how you're adding like 2 more extra polynomial identities inside the proof. So to summarize for the cost of a lookup argument, so first like you need to oh yeah, so I forgot to do that. Like when you do this multi-set check, you are going to construct another column like the ZT column, which is like Z column here. I forgot to mention here. So this is going to help you to, this kind of helper. So I kind of had way beyond that because there's a lot of math behind that. But just you create like a new column to check this running sum check. That's going to constrain this permutation check. So that's why in total you have if you have DT lookup arguments inside your circuit, you will need to add additional 3 DT polynomials or columns you need to construct. So that those kind of are virtual columns which doesn't exist in your original circuit. And then you will have additional 4 DT polynomial identities, those like 4 constraints you have in your final proof. Okay, so now let's take a look at what happens when you generate the proof like in the Halo2 plus the KZG provers. So first of all, like in the first phase, so we define like there are 4 phases in total. So the first phase is that you are going to assign, like given the input data you have, you need to assign all of the values into your giant 2-dimensional matrix. I would call the witness assignment. And then next things you are going to do is for every column inside your circuit, including all of the advice column, fixed column, like instance columns, etc., and permutations, you are going to commit them. You first need to convert them into polynomials, and then you will do some commitment using whatever commitment scheme you are using inside your provers. So like we call like the commit, like the fx at all of those things. And then the second phase is going to do like some extra processing for the lookup arguments, which you need to generate, construct all of the a prime x, t prime x, and the ztx that's going to use to constrain this lookup arguments. And then for all of the additional polynomials you generated, you also need to generate some commitment. You need auto commit all of these extra additional columns there. And in the third phase, what you're going to do is you need to compute the giant quotient polynomials, which you include all of the custom gates constraints, and then all of the lookup arguments constraints, and the computation arguments there, and then create a giant quotient polynomials, and then with some random linear combination of all of the polynomials you have, identities you have. And then, so that's like the h prime x, which is the hx divided by the xn minus 1, which means that this original hx should hold to be true for all of the value from the 1 to n you have. And then, because this h prime x, the degree of the h prime x is pretty high, depending on like the highest degree you have for all of your custom gates and the lookup arguments. So you are going to slice this h prime x into like the certain number of the slices, and each slice of the polynomial will have the degree up to n for each degree for each polynomials. And then here, how many slices here is the 2 to the extended k minus k, where this extended k is kind of the, so this difference between the extended k and the k is determined by the highest degree for all of the polynomial identities. So in terms of what's the degree, for example here, this L0 times zx minus 1, the degree of this polynomial identity is 2, because you have at most like L0 times z, so that's 2 polynomials multiplied together. So that's kind of the degree called like the degree of all of the polynomial identities. So here the difference is here is the highest is determined by the highest degree of all of the polynomial identities you have. And then you also need to commit all of the slices sliced hi prime x polynomials here. And then the last thing what you do is going to do the openings of all of the polynomial you have at the random points and all of the rotations you have. The rotation here is meaning you create like at the current row or the next row or the next second rows, those kind of are the rotations. And then you will use this multi-open protocol at the final to do the pairing check, like those kind of things, running some multi-open protocols. So these are the 4 phases you happened in behind of the provers when you do the proof generation. Any questions so far? No. Okay. So next, I'm going to talk about the different types of computation you happen inside proof generations. So the first is the witness generation, which is just only like in the finite field, you do a lot of computations and then filling them into this 2-dimensional matrices to do like an assignment. And then second, what you're going to do is you need to convert all of the point values between the point values into the polynomial coefficients. That's how you get like a column of values and then convert them into a polynomial, which you apply, the operation you apply here is doing the IFFT to do that, and then you do the IFFT you use the IFFT to convert from point values into the polynomial coefficients, and then use the FFT, or maybe like I'm wrong about that. So anyway, so like you use like these 2 operations to convert between these 2 things there. And then the next thing is like you need to do some polynomial multiplications and divisions. So those are the vector operations, which means like if you have convert your polynomial into those point values, then you just only need, what you need to do is you multiply those point values together so those are like all the vector operations. And then the fourth is like do the polynomial commitment. Here, because we're using the KZG, so we are just using the MSM operations on the elliptical curves you have, like you choose for the KZG. And the last things like you do is like open polynomial and the random points. And then one more thing is you probably run some the multi-open protocols there. So those like the open polynomial at the random points is that you're given a scalar value, and then you evaluate your polynomial with all of the coefficients you have inside the polynomial, and you can calculate what the value the polynomial evaluate at a certain x you choose, at some random x you choose. So let's see what happens, what kind of computation is involved in each phases. So in the phase 1, which we do the witness assignment and then some pre-processed columns. So that kind of computation you do is witness generations and the MSM, FFT, and IFFT. So MSMs, which is you need to use to commit a polynomial, and the FFT and IFFT is which you need to generate some of the, you need to convert the original columns into different values and then different coefficients. And then second, in the lookup arguments or the computation you do, the first things you need to construct these permuted columns, which I described before. And then you also need to do the MSM and IFFT. And the third things for the computer quotient polynomial, what you need to do, a lot of things is to do the polynomial multiplications and divisions so that you can construct this final quotient HX polynomials. And they also do some FFT here inside phase 3. And then the phase 4, which evaluates the polynomial at the random points and the random multi-open protocol, what you need to do is to do the polynomial evaluations, the multi-open protocols, and then some MSN you need to do inside phase 4. Okay, so that's all about all of the prover, what prover does in behind. So next I'm going to talk about some optimization for the zkEVM we did so far. So this is the previous graph we did. So actually there are two different types of the circuits here. So one is all of the circuits inside the zkEVM. So those circuits, they just generally have more custom gates, more lookup arguments, but fewer rows. And then another type of things is the aggregation circuit, which have more rows and then fewer custom gates and then lookups. So take an example to compare the EVM circuit we have so far, and then versus the aggregation circuit we wrote. So the EVM circuit, we use 2 to the 18 rows inside our circuit. That can handle around about 1 million gas. You can have to handle that. The gas is in that EVM gas. And then you have 116 columns inside that. But at total, you have almost 2,500 different custom gates and then 50 lookup arguments. And then the highest custom gate degree we currently have is 9. But there's also adjustable, so you can have some config. You can change it to a smaller value like 5. But currently we just use the config as highest custom gate degree is 9. And then if you want to handle more gas inside the event circuit, then you need to have more rows. For example, if you have 2 to 19 rows, then you can probably handle 2 million gas. And then in comparison, the aggregation circuit we have is 2 to 25 rows. Because we need to aggregate all of different circuits inside one aggregating circuit. That requires do a lot of ECC operations inside the aggregation circuit. Right now we need to have the 2 to the 25 rows to aggregate all our proofs we have inside the zkEVM circuit. And then you have 23 columns and 1 custom gate, 7 lookup arguments, and then the highest custom gate degree is 5.
Haichen, we have a question.
Yeah.
So many custom gates, right? Is there a selector per custom gate? Because it seems that you don't have 2,498 columns, right?
So you share a lot of selectors across different custom gates. For example, we have one gadget, almost one gadget for each opcode, and then but inside each opcode you have different, you have multiple custom gates corresponding to that gadget, and then one gadget is usually constrained by 1 or 2 selectors to constrain that custom gate. So
yeah.
Gadget, yeah.
Yeah, it's you implemented the opcode switching.
Yes.
Without having to use 2,500 selectors,
right.
Basically.
Yeah.
And then does that columns count also include for lookup arguments the virtual A prime T prime?
No.
Okay.
This is the original columns you have. So if you want to see so for this you will end up around 300 columns after you counting down all of the additional columns you need to have and the points you have. Okay, so now let's look at some performance numbers. So if we run this for the event circuit case study, look at example of the event circuit. So if you do the proof generation on the CPU using the Halo2, So right now we are benchmarked on the AWS G5 12x large instance, which have 48 CPU cores and then 192 gigabytes of CPU RAM, and then there's 4 NVIDIA A10G GPUs. So if you're running like everything inside the CPUs, that's the amount of the time you need to spend in each phase, and then the total amount of the time you have for the proof generation is about like 4.5 minutes to generate for the EVM circuits. And then, so the first optimization we did on top of the CPU is trying to move the MSM, IFFT, IFFT into the GPU kernels, which you involve, like, for example, phase 1, you have like these things like so actually every phases will be involve some of the things that will be happening inside the GPU instead of inside the CPUs. And then now let's take a look at what happens after you apply these GPU kernels, where you can see like the phase 1, the most of the time is spent is on doing the MSM or IFFT stuff. And then so you can reduce that from 70 seconds to down to the under 5 seconds. And then so it counts like all of the things up. Then now the proving time is about like under 2 minutes. So you can achieve like a 2.5, 2.4x speed up. So and then this is using the 4 GPUs. So you can evenly distribute like the different FFTs into different GPUs, and then different MSM to different GPUs. So that's like utilizing all 4 GPUs on this AWS instance. And then so next things we realize is like now the bottleneck, the most time spent is in the phase 3, which is the highest time. What phase 3 does is not only the FFT, so it also does those polynomial multiplications and divisions. So it also can be very easily to be parallelized using the GPUs. So like the second thing optimization we did is to compute those quotient polynomials inside GPUs. And then so now you can see that you can halve the time you can spend in the phase 3 from 33 seconds to 28 seconds, 28.7 seconds. And then the third thing like that, so right now I think like the third thing we did is to, in the phase 2, there are certain part of things like construct the permutate columns for all the lookup arguments. That's happened like they're still down in the CPUs. But like if you can parallel pipeline the CPU part of the things with the GPU. So like when you construct the current, when you're doing the MSM or IFFT for the new columns you generated for this lookup argument, then at the CPU you can also to construct permutate the new columns for the next lookup argument. So I'm doing like this pipeline stuff to optimize the phase 2. And then what you get is like in the optimizing 3, you can decrease the phase 2 from 23 seconds to 5.9 seconds. And then so the total time, like now, if we want to generate the proof for the the EVM circuit is like around 58 seconds. So it's like below 1 minute. And if you compare that all the optimization we apply with the original CPU ones, they achieve like almost like 5x speed up comparing them using the CPUs. Any questions so far? Okay, so, oh wait, oh yeah. So next, like just take a look at it. For example, like, sorry, there's one question.
Yeah, sorry, and is this for proving like one, like validation of one block of transactions?
Yes.
Or, okay.
Yeah. Okay, so next, I want to look into details of like how much time you spend inside MSM and the FFT, IFFT. Like if you're in the CPUs, you can think of like, you can take a look. So that almost like 64% of the total time will be spending doing like the MSM, FFT, IFFTs, which you can say like this is like some rough number there. But if you want to look at it into GPUs, right? So in the GPUs, takes the latest optimization you have here. You can find like actually after you moving all of FFT and then IFFT, MSM into the GPU kernels, now the total time you spend in the GPU for those operations is only like around 16% of the total proof generations. And then the rest of them actually now becomes all of the 58% of time. Although like here in the phase 3, this part of like 25 seconds is doing the polynomial multiplication divisions. That also mostly happen inside the GPUs. So but the rest of them you can see like so currently we haven't moved this like multi-open and then polynomial evaluation into the GPUs. So those part of things could be like the next target to further optimize to reduce the proof generation time. Okay, so but like on the other case, like for the aggregation circuit, now we also did like the similar optimization to the aggregation circuit, and then now you can find actually because the aggregation circuit, the differences between the aggregation circuit versus the EVM circuit is that aggregation circuit has more rows and then fewer custom gates. Now you can find that the phase 1 takes now the most of the time in all of the proof generations. So it takes like almost like 2 minutes in the phase 1. So what happens like in the MSM and FFT, it doesn't take a lot of time. That's like almost like 2 minutes. What it's doing is doing the witness assignment. Because you have a very large circuit and you fill them like one by one, row by row. So it takes a lot of time like inside the CPUs. That's saying something like we're continually optimizing and working on to improve that, to see if we find any way to parallelize this proof generation witness assignment inside the CPUs to utilize multi-cores. And then you can see like in the phase 3, which does like a lot of polynomial multiplication and divisions, that actually is less time than the EVM circuit because it has less custom gates so that you have fewer polynomial multiplications you need to do like operating in the phase 3. Okay, so there's some quick summary. We have like some takeaway we have from all of the optimization and then the comparison, like things like. So the FFT and the MSM is still like dominating time if you're using the CPUs. Although currently like we're not sure. Definitely probably we haven't heavily optimized the FFT and the MSM in the CPU. So that could be like some hand-wavy claim we have because we haven't really optimized that because we spend most of the time just optimizing the GPU kernels. So, but it could be still the case, like FFT and MSM could be dominating if you don't use the GPU kernels, but that won't be the case actually for if you have the GPUs, because it only adds up to 16% of total time. And then, so for the large circuits, the witness generation is really kind of a bottleneck for the proof generations you have. And then for different type of circuits, like you have different characteristics for different circuits. So you need to apply some different optimization to different circuits. So in the aggregating circuit, more rows lead to higher cost of large FFTs. So you need to have better large FFT kernels in the GPU. And the EVM circuit actually has lots of custom gates, so that you need to do better polynomial multiplications and probably polynomial evaluations better to do that. And then so that you need to tune the performance based on different circuits layout. Okay, so previously it's all about our the proof optimization we did so far. And then we'll continue working on that. So next, I'm just going to talk about how we want to build our decentralized proven network. Yeah, so this is the kind of the architecture I showed before. So we have this decentralized proven network so that everyone can join and build that. But how we are going to reach to that goal, like the final goal there. So I think right now, what we're doing like in the stage 1 is we build a GPU solution for generate proof of the zkEVM'S circuits. And then we're going to build so right now we're using some AWS instances for the proof generations, but we'll also build some private GPU clusters to provide a more stable and then cheaper solutions for building for the proof generation power on our testnet in the stage 1. But the next stage we're going to do is we're trying to collaborate with some hardware partners and companies, and then to see how we can share our results so far, and then share our proof systems and our optimization some profile we did, and then to see how we can work with them together to build a better customized hardware accelerators. And I believe that with better custom provers, you can still can improve, shorten the proof generation time. With you can see how we can do better parallelize on the rest of part we currently spend in the CPUs, and then how to make the MSM and FFT even faster than the GPUs. And then at the stage 3, our plan is going to definitely open source our GPU provers we have so far, and then probably we'll have some add up a little bit more optimizations with some permissionless license so that everyone can use as some baseline, so you can run a GPU server yourselves to become our prover, a roller to join our decentralized network. And then, so if at that time we see if there's some solutions from the hardware company, so that people can also buy those custom hardware from those hardware companies, and then to use that as their provers in parallel. So yeah, so that's pretty much like what I want to say about our decentralized prover networks.